Okay, before we go into question number two, let's kind of have a brief run through of runtime analysis. Okay, big O denotes asymptotic upper bound. For function f to be equals to big O function g, this means that function m like runs longer than like 0 time, but it definitely grows slower than some function gm times c for some constant c. Big omega, it is an asymptotic lower bound. For function f equals to big omega function g, this means that function f not only runs like takes more than 0 time to run, but it also runs longer than some function g times some constant c. Okay, and big data, it is a type bound. By type bound, it means that function f is both equals to big OGM and big omega GM. This means that it is both upper bounded and lower bounded by a function g. Okay, so for question 2, we are given 3 different functions, and we know that function f runs in big data linear time, and function g runs in big data quadratic time, and this runs in big O quadratic time. We also know that each function takes in an integer array as its input and output an integer array of the same length. Okay, so we are then given part A method. A quick glance through the method body. The parts that can be candidate cost model would be this line, the for loop, and the last 2 lines before the return statement. Okay, since we know that among the 3 functions f, g, and h, f is the absolute lower bound, right? It runs in big data linear, so it will be the smallest when compared to all the quadratic models. In that case, we can ignore this line. And for the for loop, we know that it iterates through the 3 arrays, that is x, sugar, and spice for n times to update the n indexes, the value at the n indexes of the spice array. So we are pretty sure that this will be a big data linear function. So we can also ignore this. So for these last 2 lines before the return statement, an integer array of length n that is named spice is being fed into function g, which runs in big data quadratic time. And afterwards, this output is further fed into function f that runs in big O quadratic time. So at this point, we are pretty sure that the cost model must be a quadratic function. However, would it be big data quadratic or big O quadratic? Using the big data notation, it informs us that part A method will be lower bounded and upper bounded by the quadratic model. Each already accounts for the fact that it will be upper bounded by a big O quadratic, right? So this is a much more informative and inclusive notation than big O quadratic. So we can just drop big O n squared and keep big data n squared. And this will be our answer for this question. Okay, for part 2.2, we are analyzing the runtime of each of the following line in the method body of part B. Okay, so for the first line, we run function f on input array x to get an integer array, and we know that function f has a type bound So it will just be tether, and that is pretty direct. And for the second line, it is a nested function. To get the weekend integer array, we see a nested functions both involving function f. Again, it would be the tether n. And for the third line, it is a nested function involving function g. And function g, as compared to function f, it has a higher cost model that is a quadratic type. So this line must be a quadratic model. And we have, and like function g, we have a tether bound for it. So it will be tether quadratic. For the fourth line, the cost model would be determined by function h because it is also a higher power function that runs in a quadratic model. So we will just a quadratic model and a linear model. And for this quadratic model, we don't have a type bound for function h. We only have a big O bound, right? So it will just be big O quadratic. And for the last line, this nested function involves all three functions. We can drop the lower power linear model and just consider a quadratic model directly. And we have a big O bound for function h, but we have a big tether bound for function g. And both of them, and both function h and g, they run in quadratic model. And again, like as explained in part 2.1, the big data bound is more informative. It informs us that this operation is both lower bounded and upper bounded by a quadratic model. So we will stick to the informative bound that is tether and square. And that's it. Thank you.